Hello everyone. In this tutorial video we are going to talk about how to perform scientific calculations in an honors course. And this video is going to address two major topics, and those are significant figures and their use in calculations, and dimensional analysis, which my very first chemistry teacher taught me to call railroad tracks, and which I still call to this day. So to get started with the rules for significant figures, there are two situations which we will address. The first is when multiplying or dividing, and we are directed to keep the smallest number of significant figures provided in the problem in that situation. So you will go through all the numbers provided by the problem, identify the number with the smallest number of significant figures, and maintain that number in your answer. The other situation is when adding or subtracting. In a similar structure, we are directed to keep the smallest number of decimal places provided in the problem. So again, we'll go through each number in the problem, identify the number of decimal places, and round our answer so that it has the right number of digits. We'll start with a few examples. Our first example is 8.32 plus 1.2. When you plug this into your calculator says 9.52 is the answer. So now we need to look at our significant figures. Remember that the rule says that we're supposed to keep the smallest number of decimals provided in the problem. So here 8.32 has 2 decimals, but 1.2 only has 1 decimal. So that means we are going to be keeping 1 decimal place in our answer. So we'll have our 9, and then we'll have our 0.5, but that's all we're allowed to keep. So in order to help us decide which way to round, we're going to look at the 2. Just like in math, 5 and above rounds up, anything less than 5 rounds down. So this means that we're going to be rounding down, and we are going to report our final answer as 9.5. Again, maintaining the 1 decimal place that we had in our problem. For some multiplication division examples, we have 2.25 times 3.1. When we type that into the calculator says that the answer is 6.975. But we need to look at the significant figures and decide how to round that answer. So 2.25 has 3 significant figures, because all of the digits are non-zero, so that's fairly straightforward. But 3.1 only has 2 significant digits. Again, all the digits are non-zero, so it's fairly easy to identify that they are significant. So this means our answer can only have 2 significant figures. So we'll have the 6 and we'll have the 9, but then we'll have to decide which way to round. Again, we're going to look at the next digit and decide which way to round. A 7 is greater than 5, so it would tell us that we're supposed to round up. When we round 6.9 up, we get 7. But that does not meet our requirement of 2 significant figures from the problem. So we will need to add 0.0 in order to maintain those 2 significant figures provided in the problem. And so 7.0 would be our final answer for this multiplication problem. Another multiplication example, we have 7.50 times 1.2. When we plug that into our calculator says that the answer to that problem is 9. But again, we need to look at our significant figures so that we can report our answer accurately. 7.50 has 3 significant figures, because the 0 is to the right of both the decimal and the number. 1.2 only has 2 significant figures. So this means that we are supposed to report our answer with 2 significant figures. The calculator just gave us 9. So just like when we were talking about 7 and didn't have enough significant figures, we are going to have to report our answer as 9.0 so that we have the appropriate number of significant figures in our final answer. So those are the rules for using significant figures to round your answer in a scientific calculation. Now we're going to look at dimensional analysis. Dimensional analysis is most helpful in multi-step multiplication division problems, and it is generally only used when we are doing multiplication and division. So here's an example problem. We have 2.5 milliliters of a 7.25 gram per centimeter cubed material. We're going to start our work by drawing a large horizontal line and placing the number that is not a ratio in the upper right-hand corner of that line. Instead of writing a multiplication or division symbol, we're just going to draw a vertical line separating that term from the next set of terms that we're going to put into the problem. Now, I would like to use 7.25 grams per centimeter cubed as my next set of terms. However, no part of that will cancel out the milliliters. In order to cancel out the milliliters, I need to use my prior knowledge that 1 milliliter is equal to 1 centimeter cubed. I can put that ratio into my railroad tracks by saying that 1 milliliter is equal to 1 centimeter cubed. And I have flipped the ratio specifically so that milliliters will cancel, because I already had milliliters in the numerator. Now it's in both the numerator and the denominator, so it will cancel out. Now I have centimeters cubed, and I can plug in my density ratio, 7.25 grams for every 1 centimeter cubed. Again, notice I arranged my ratio so that the units that I'm not interested in will cancel, in this case centimeters cubed. This leaves me with grams. Since grams are the only unit that haven't canceled, they're going to be the unit of my answer. My calculator says that the answer is 2.5 times 1 times 7.25 divided by 1 is 18.75 grams. And for those who didn't quite catch, I am multiplying across the top and then dividing by the denominator. Now that I have my calculator answer, I can go back and look at my significant figures. 2.5, of course, has 2 sig figs, whereas 7.25 has 3 sig figs. Since I'm supposed to maintain the smallest number of sig figs in my multiplication division problems, I'm going to need to round my answer to have 2 sig figs. So I'll have the 1 and the 8, and then I can look at the 7 and decide which way to round. Because 7 is greater than 5, I'm going to round up, and I will report my final answer as 19 grams. So here we did our multi-step multiplication division problem, and then rounded to the smallest number of significant figures provided in the problem. Here's another example of a problem in which dimensional analysis is helpful. How many meters cubed in 2.50 centimeters cubed? Now, centimeters cubed is an example of a compound unit. And a compound unit is just a combination of smaller units that is being treated as a single unit. In this case, the smaller units inside of our compound unit are centimeters times centimeters times centimeters. So when I prepare to write out my railroad tracks, and I draw my long horizontal line, and I put my number from the problem that's not a ratio, I'm not going to write centimeters cubed. I'm going to write centimeters times centimeters times centimeters. And the reason for that is that during my conversion, I must cancel out each of these 3 centimeters in order to convert from centimeters cubed to meters cubed. I can't just use a single copy of 100 centimeters in every 1 meter, because that only cancels out 1 of my centimeters. I have to use an additional 2 copies of this fact in order to cancel out the additional centimeters from my centimeters cubed. Notice that this leaves me with meters times meters times meters, or the meters cubed that I'm asked to find in the problem. When you type this into your calculator says that the answer to this question is 0.00025 meters cubed. Now we need to check for significant figures. The only number provided in the problem is 250, and it has only 2 significant figures because this 0 is not to the right of the decimal. So that means that our answer is supposed to have 2 significant figures, since that's the only value that we have. So when we come over here, we have all of these lovely zeros that are to the left of the number. And the only significant figures are, again, the 2 and the 5. So our number of significant figures has automatically been conserved because we are just converting between units and not really doing any multiplication or division. Our final example is another compound unit. In this case, kilometers per hour. So when we go to write our railroad tracks, we're going to draw our long horizontal line, and we're going to plug in 40 kilometers per hour. So 40 kilometers for every 1 hour. In this compound unit, I have a unit in the numerator and in the denominator. Both of them we have been directed to change. Hours into seconds and kilometers into meters. So I'm going to do the hour into seconds first because that is the one that I'm most familiar with. So for every 1 hour, there are 60 minutes. And when I write in that ratio, I will cancel out hours. Then for every 1 minute, there are 60 seconds. And when I write in that ratio, I will write it so that minutes cancel. So right now I have kilometers per second. And now I just need to change the kilometers into meters. So I'm going to pull up in my mental database that 1 kilometer is equal to 1,000 meters. And that will allow me to cancel out my kilometer units, leaving me with meters over seconds, or meters per second. When I plug that into my calculator, it says that there are 11.111 repeating meters per second. And I definitely don't want to report a repeating number as my final answer. So I'm going to go back to my problem and look for the number of significant figures. In this case, 40 only has 1 significant figure because the 0 is to the left of the decimal. And since I've done all multiplication and division, I'm going to need to conserve that 1 significant figure in my final answer. So I'll get to keep my 1 in the tens place, and then I have to round based on the digit behind it. A 1 is less than 5, so it's going to round down. And so I will report my final answer as 10 meters per second. Again, this 0 is not significant because it is to the left of the decimal. So 40 kilometers per hour is the same thing as saying 10 meters per second. Alright folks, in this video we have talked about how to perform scientific calculations, in particular paying attention to the rules for significant figures, both the rules for multiplying and dividing and the rules for addition and subtraction. We have also talked about how to use dimensional analysis or railroad tracks. Thank you very much and have a nice day.